All right, settle in, because today we're embarking on a really deep dive into something truly fascinating. We're talking about the intricate world of drift car suspension setup.
Yeah, it's a deep rabbit hole for sure.
You know, those incredible moments, a car just gliding sideways, tires smoking, but it looks like effortless control.
Mm-hmm. Controlled chaos, they call it.
Well, beneath that surface, there's just an incredible amount of science, engineering, and serious fine-tuning going on.
Absolutely. It's not just about sliding, it's about sliding well.
So we've gathered insights from, like, the best in the business pro drivers like Chris Forsberg, Chelsea Denofa, Dio Shihara.
And engineering heads too. Jason Fensky, builders from FDF Race Shop, Pernstar, Network A, Racecraft HQ, solid sources.
Right. Our mission for you today is basically to extract the most important nuggets of knowledge from all this,
Yeah.
give you a shortcut to understanding what it takes to make a car dance on that edge of grip and slip.
Get ready for some serious aha moments because, yeah, this is where it gets really interesting.
Okay, so let's kick things off. What is a drift car actually trying to achieve? It looks wild, but there's a goal, right?
Definitely. The core objective, really, is controlled oversteer. You're purposefully braking traction, getting the rear end to step out.
But then holding it there at a specific angle.
Exactly. Maintaining that angle while still moving quickly and, crucially, with precision.
Which is totally different from, say, grip racing.
Oh, completely. Night and day. In grip racing, you want maximum traction. Stick to the road, minimize any slip.
Drifting, though, you're embracing the slip, manipulating.
You're making it work for you. It's a dance.
But here's something that seems like a contradiction. If you're breaking traction, why do we keep hearing things like grip equals speed, even in drifting?
Yeah, that trips people up. It sounds paradoxical, but it's fundamental. While you are sliding, the car still needs to generate enough mechanical grip to actually, propel itself forward.
Right, otherwise you'd just be spinning in place.
Exactly. You'd look cool for a second, then go nowhere fast. So you need enough grip, particularly from those rear tires, to push the car, to accelerate, to maintain momentum while sliding.
So it's not just about making it easy to slide.
No, the ultimate goal is to slide fast and controllably. That requires managing grip even in the slide.
And that ties into another point that came up a lot, making the car easy to drive. Why is that so important? Seems like pros could handle anything.
Well, think about it. If the car is predictable, if it does what you expect it to do, it frees up your mental energy.
Ah, okay, so you're not constantly fighting it.
Right. Instead of wrestling the car just to keep it sideways without spinning, you can focus on the critical stuff, your line, your timing, your throttle adjustments, anticipating the next transition.
Makes sense. A comfortable, predictable car lets you push closer to the limit more consistently.
Exactly. You're faster because you're confident. You can place the car exactly where you want it.
Now, inside this world of setup, there's this constant theme of trade-offs. Like, every adjustment is a give and take.
Oh, absolutely. There are no magic bullets in suspension tuning. No absolutes.
Optimizing one thing often means compromising somewhere else.
That's the balancing act. You're always trying to find that sweet spot. You need enough rear grip for forward drive.
But you also need a front grip, so you can actually steer the car precisely while it's sideways.
Exactly. And you're balancing how easily the car rotates into a drift versus how stable and predictable it is once it's in the drift.
And it's not like making something infinitely soft or stiff gives you infinite grip, right? There's an optimal range.
Precisely. That's the sweet spot concept. Go too far in either direction, stiffness or softness, and performance actually drops off.
Can you give us a concrete example? Like you mentioned, dialing in more rear toe in for better drive. What's the give for that take?
Okay, good one. So yeah, add rear toe in, the tires point slightly inwards. They kind of fight each other a bit.
Which plants the rear, gives you that
Right,
foray.
guy, especially driving out of the corner, under throttle. Huge benefit there. But the trade-off,
The guess.
Yeah.
Tire wear.
bingo. Because those tires are scrubbing against each other and the pavement while sliding, they generate a lot more heat and wear down much faster.
Ah, so you get the drive, but you might cook your tires way quicker.
Exactly. So you have to decide, is the extra drive worth burning through tires faster? Depends on the track, the rules, your budget. It's always a calculation. Maybe you also lose a tiny bit of ease in initiating the slide, but the big one is usually wear.
Okay, so that's the philosophy.
Yeah.
But before we even get to tweaking angles and springs, you need a solid base.
Foundation first. Always.
We saw that perfectly with Chris Forsberg's 72 Datsun 510 wagon build. You know, he said a 45-year-old car is bound to have some rust.
Understatement of the year for some project cars.
And his team went deep. Cutting out all the rust floor, firewall, trans tunnel. That seems like bodywork, but how does that directly impact suspension tuning later?
Think of the chassis like the skeleton. If your skeleton is weak or flexible, your muscles can't work effectively.
Okay, makes sense.
Same idea here. If you mount your fancy coilovers to a rusty, flexing frame rail, what happens?
The suspension points move around.
Exactly. All your precise damping, your spring rates, your alignment settings, they become meaningless because the points they're attached to are shifting unpredictably. That chassis flex eats up grip, kills consistency.
So that horrible, no fun task of cutting out rust is literally building a stable platform so the suspension can actually do its job predictably.
Precisely. Every force, every bump, acceleration, braking it needs to go through the suspension components, not get absorbed by a twisting chassis.
And they had some cool techniques like using a piece of copper behind holes when welding.
Yeah, that's a neat trick. The weld won't stick to the copper, so you can build up the steel around the hole, then grind it smooth.
Again, meticulous detail. How does that tie back to performance suspension?
It's all about structural integrity and consistency. Every single weld, every seam needs to be rigid. Any weak point, any old hole that could allow flex introduces inconsistency. Your suspension might not react the same way, corner after corner, run after run. And for a driver relying on feel and predictability, that's a killer.
They also focused on the driver environment, adding Dynamat for sound deadening after putting in new floor pans, avoiding that tin can inside the car feel. How does comfort play into performance driving like drifting?
It's huge for feedback and reducing fatigue. If you're being bombarded by noise and vibration, it's distracting.
You can't focus on what the car's doing.
Right. Drifting relies heavily on feeling subtle cues, the tire starting to slip, the chassis rotating, the grip level changing. If all that is drowned out by noise, your reactions are slower, less precise.
So a quieter, more composed cabin lets you feel the car better.
Absolutely. Better feel leads to more confidence, quicker decisions, and ultimately more consistent performance over a long day at the track. Less fatigue, too.
The engine bay prep was intense too. Filling holes, smoothing, polishing, even being careful about washing metal bits out of a water pump after drilling. Adding fancy hose fittings. It points to a bigger picture, doesn't it?
Totally. It's holistic engineering. That custom -16 weld bung for the radiator, the XRP hoses, that's about reliability under extreme stress.
Because a perfect suspension doesn't matter if the engine overheats.
Exactly. A coolant line failure, an engine issue that ends your day instantly. Making sure every supporting system is bulletproof means you can actually focus on suspension tuning without chasing other gremlins. It's about building a reliable total package.
And the brake line's new stainless steel, carefully rerouted for clearance and looks. Beyond aesthetics, why is that important for a drift car?
Brake consistency is critical. Initiation, mid-drift speed adjustments, weight transfer. You're using the brakes constantly and precisely.
So spongy or inconsistent brakes would be a nightmare.
A complete nightmare. Old flexing lines, poor routing that can lead to inconsistent pedal feel, maybe even boiling fluid. Stainless lines give you a firm, consistent pedal, run after run.
So the driver knows exactly how the car will react when they touch the brakes.
Yes. It allows them to use braking confidently as part of their driving technique, a tuning tool almost.
Okay, so chassis is solid, supporting systems are reliable, then you get to the drivetrain and braking upgrades.
Yep, can't ignore those. They pulled the factory diff and its flimsy mount for an upgraded rear end. Why is the diff so critical? It's the link between engine power and tire rotation. A weak diff or mount can cause wheel hop, inconsistent power delivery, loss of drive mid-drift. Basically, you can't put the power down controllably.
So a stronger diff and mount mean reliable, consistent power to the wheels.
Exactly. And brakes, yeah, old cars often have very outdated brakes.
Which is scary when you add a ton of power and grip.
Seriously scary. Upgrading to something like Willwood vented rotors, better calipers, maybe those Techno toy tuning billet hubs, it's essential for stopping power and, just as importantly, resisting brake fade after repeated hard use. You got to slow down as well as you go sideways.
All right, foundation laid. Now let's get into the pillars. Springs, shocks, and sway bars. This is where the real handling magic starts, right? The dance of control and grip.
This is the core of it, yeah. Springs primarily manage the car's vertical movement, that dive under braking, the squat under acceleration.
And the shocks, or dampers, they control the speed of that movement, stop the bouncing.
Precisely. They slow down the spring's oscillations, keeping the tire pressed firmly against the road surface as much as possible. Consistent contact is key.
Now, one big difference for drift cars. Generally, a softer rear suspension setup.
Yeah, that's a common philosophy. A softer rear encourages more weight transfer to the rear tires during the slide.
Which seems counterintuitive, but it maximizes mechanical grip back there.
Exactly. More weight pushing down on those rear tires helps them dig in and find traction for forward drive, even while they're spinning. It maximizes propulsion.
Chris Forsberg had a great breakdown of street car versus track car setup here. Track car. Absolute extreme with the softest spring possible in the back, but with a very stiff shock to control it. Why that combo?
Okay, so the super soft spring allows for maximum weight transfer, really loading up those rear tires for grip, but a soft spring alone would just bounce uncontrollably.
Like a waterbed on wheels.
Pretty much. So the very stiff shock is crucial. It precisely controls the rate of compression and rebound. It settles the car quickly onto its rear tires and stops any oscillation or porpoising that would break tire contact. It's about control of the softness.
Whereas his streetcar setup is a little bit stiffer of a spring for bumps and not as stiff of a shock for better ride quality.
Right. Street setup prioritizes absorbing road imperfections without bottoming out, and a softer damping lets the wheel move more easily over bumps for comfort. It's a compromise for daily driving. Track setup ruthlessly prioritizes that instant load transfer and grip in high G situations.
And here's a factor people miss. Motion ratio. It's not just the K rate on the spring box, right?
Oh man, motion ratio is huge and hugely overlooked sometimes. It's basically the mechanical leverage the wheel has over the spring.
Meaning the wheel moves more or less than the spring actually compresses.
Exactly. Like on a Miata, a 10K front spring might only feel like a 7K spring because the motion ratio is maybe a 0.7. The wheel moves 1 inch, the spring only compresses 0.7 inches.
So that same 10K spring would feel way stiffer on a car with a different suspension geometry.
Absolutely. A 24K spring on an IS300 feels totally different than on a 240SX. Weight matters, but the suspension design McPherson strut versus double A-arm or multi-link drastically changes the effective spring rate at the wheel.
So you can't just compare spring K rates between different cars.
Nope. Gotta understand the geometry and motion ratio to know how stiff it'll actually feel and perform.
Okay, shocks. Most coilovers have damping adjustments. We hear start in the middle is a good baseline. But what are you feeling for when you adjust it? Too much or too little damping?
If you have too little damping, the car feels floaty, bouncy, like a pogo stick. After a bump or a weight shift, it keeps oscillating. Very unstable. Tire contact is inconsistent.
Okay, unsettled and too much.
Too much damping, and the suspension feels harsh, locked down. It won't absorb bumps well. The tire might skip over rough patches instead of following the contour. Lots of grip again.
So you're looking for that sweet spot where it settles quickly, feels controlled, but still absorbs bumps.
Exactly. Quick settling, keeping the tire glued, but without being overly harsh.
And that trackside trick, the zip tie on the shock shaft.
Yeah.
You do a few laps, check where it moved. If it's slammed to the top.
You're bottoming out. You've used all your available shock travel.
And that's bad.
It's catastrophic for handling. The suspension effectively becomes a solid block at that point. No more bump absorption, no more controlled weight transfer. The tire instantly loses grip, the car becomes super unpredictable, harsh.
So even if your alignment's perfect, bottoming out ruins everything.
Everything. The zip tie tells you need more spring rate, need more ride height, or maybe need to adjust your bump stops to engage sooner or differently.
Okay, springs and shocks handle vertical stuff.
Yeah.
But what about body roll when you chuck it into a corner? That's sway bars or anti-roll bars.
Yep. They're torsion springs connecting the left and right suspension. Their main job is to keep the car level, control that body roll.
How do they do that?
When one wheel compresses in a corner, the sway bar twists, and it uses force from the unloaded side spring to help resist the roll on the loaded side. It actively fights the car's lean.
And for drift cars, the strategy is usually different front to rear.
Generally, yes. You often see a really stiff front sway bar. Why? To keep that front end planted while the car's sideways. Helps maintain front grip for steering control during the drift.
Makes sense. And the rear.
Usually slightly softer one in the rear, or sometimes even the stock one. This allows a bit more controlled body roll at the back.
And that actually helps. How?
That controlled roll can help catch the car from going into a spin. As the body rolls, it shifts weight dynamically, sometimes momentarily increasing grip on the outside rear tire, stabilizing the slide.
So the rule of thumb.
Yeah.
Big, stiff front sway bar. Soft, like stock rear bar. Some bros even run no rear bar.
Yeah, some do. Removing it allows maximum independence for the rear wheels and maximum weight transfer via the spring shocks alone.
But there are downsides.
Oh yeah, it can make the car feel less responsive to inputs, kind of sloppy sometimes, especially with really soft rear springs. You get these really weird characteristics, potentially puts a lot more burden on the rear springs and shocks to manage everything.
The cool thing about sway bars is adjustability. Those multiple mounting holes on the end links.
Right. Changing where you attach the link changes the leverage the suspension has on the bar. It's an easy way to fine-tune the bar's effective stiffness right there in the pits. Small adjustment, noticeable feel change.
So why are they so crucial? Why not just crank up the spring rates to reduce body roll instead of using sway bars?
Ah, the classic question. Because springs and sway bars do different jobs, primarily. Springs manage vertical loads, sway bars manage lateral load transfer and roll. If you make your springs super stiff just to control roll, the car becomes harsh vertically. It might skip over bumps, reducing overall grip because the tire can't follow the road surface. It might surpass its slip angle too quickly, leading to understeer.
So trying to make springs do the sway bar's job compromises vertical compliance and tire grip.
Exactly. Sway bars let you control roll while keeping the springs at a rate that allows the tires to maintain optimal contact. They're essential for balancing roll stiffness and grip.
Okay, foundation solid, springs, shocks, bars understood. Now, the really precise stuff. Alignment. Camber, caster, toe. This is where the magic happens for pointing the car, right?
Absolutely. Alignment is super crucial. It's amazing, like you said, a lower power car with a great alignment can run circles around a high power car with a bad setup.
It's all about maximizing that tire contact patch.
Every single time. That's where the rubber meets the road, literally.
Let's start with caster. That's the angle of the steering axis from the side view. Line tilted back towards the driver is positive caster.
Correct. And you experience it constantly without thinking. Bicycles, shopping carts, that front wheel wanting to straighten out, that's caster at work.
Creating that self-aligning torque.
Exactly. It provides stability, makes things want to track straight.
So how does that translate to drifting?
In drifting, high positive caster gives you strong self-steer. The wheel naturally wants to return to center or even counter-steer for you during the drift.
Which is great for those fast lock-to-lock transitions.
Huge help. Drivers talk about just letting the wheel spin it in your hand instead of having to manually crank it back, freeze them up. So often more the better is the initial thought.
But there's a limit. Too much caster, like 8, 9, 10 degrees plus. What happens then?
It can over-rotate or snap to lock way too aggressively. The self-steer becomes violent.
So the wheel just slams into the steering stops.
Yeah, it can literally whack the steering stops. Makes the car incredibly hard to drive smoothly. You're constantly fighting against the self-steer to prevent it going too far instead of guiding it. Very twitchy, very physical.
And too little caster.
Lack of self-steer, loss of steering feel. You have to manually muscle the wheel around everywhere, Arnie Palmer. Lots of effort, less feedback.
So the sweet spot is typically somewhere in the middle, like 3 to 9 degrees.
Yeah, that's a common range. S-chassis maybe 6, 6.5, E36 is around 5.5. Starting near factory and adjusting based on feel is usually the way.
And caster also causes weight jacking. Turning the wheel, lifts the outside corner, drops the inside.
Yep, significant effect. That weight transfer, lifting the inside front and dropping the outside front, actually helps unload the inside rear wheel.
Like a go-kart lifting a wheel to turn.
Similar principle. Unloading that inside rear reduces its drag, helps the car rotate more easily, maintain higher angle without bogging down. It's a dynamic tuning aid.
Wow. And adjustments are usually moving the lower control arm or using camber caster plates up top.
Those are the main ways. But watch out, extreme casters can cause over-centering, where the tie rod binds up at full lock. Nasty feeling, heavy steering, wheel wobble. Rack placement is key to avoid that.
And just to clarify, caster is mainly a front suspension thing, right?
Oh.
Doesn't really apply to the rear in the same way on race cars.
Correct. With solid bearings or heim joints in the rear, there's generally no caster angle or self-aligning torque to adjust back there. It's a front axle steering geometry parameter.
Okay, next, camber. Angle of the wheel relative to vertical, viewed from the front. Negative camber, top tilts in.
Right. And the main goal in drifting, maximize the contact patch, especially on that outside lead wheel during the turn, and get perfect tire wear.
Flatter contact patch equals more grip and longer tire life. Makes sense.
And tire life is huge in drifting. You burn through them so fast.
But camber changes dynamically, right? Suspension compresses, car rolls, camber angle shifts.
Mhm.
That's camber gain.
Yep. Some cars gain a lot of negative camber under compression, like older BMWs. In grip driving, you often want that gain to counteract body roll.
But in drifting,
In drifting, you're looking at how that camber changes at extreme steering angles and suspension travel. Too much dynamic negative camber on the lead wheel can actually hurt, making it ride on the inner edge.
so you tune the static camber to get the best dynamic contact patch during the drift.
That's the goal. Ensure maximum contact when the car is at angle.
Adjustments.
Okay.
At the spindles, lengthening the lower control arm, which also affects KPI, we'll get there, or using camber plates up top.
Right. Adjusting at the spindle is often preferred if possible, as it messes less with track width and other geometry.
Baselines, dot rear. Start at 0 static camber.
Good starting point.
Hmm.
Then watch your tire wear. If it's wearing evenly, great. If not, adjust slightly. You want maximum contact for rear drive.
And front. Steer to 60% of your angle and set that lead wheel to 0 camber.
Yeah, that's a smart baseline. The idea is to have the most critical tire, the outside front guiding you through the slide, have a perfectly flat patch when it's doing the most work, gives linear steering feel, consistent jacking.
But again, too much negative camber is bad. Reduces contact patch, less grip.
Less grip overall, yeah. Makes it easier to slide, maybe too easy, harder to control. And crucially, it just shreds the inside edge of the tire. You're only using half the tire, burning through them twice as fast. Very inefficient.
Okay, let's talk toe. Looking down from above, front's pointing in as toe in, pointing out as toe out.
Simple concept, big effects.
Front toe for drift cars. Generally, slight amount of toe out.
Usually, yes. Toe out makes the car react very quickly to steering input. Aids turn in.
Like Chelsea DeNofa suggesting 1/8 to 3/8 toe out. Makes the steering feel immediate.
Exactly. Preloads the steering response. Turn the wheel, car reacts now.
And front toe in would do the opposite. Sluggish response.
Yeah, causes a delay, requires more steering angle to get the car to turn. Not ideal for quick transitions.
But too much toe out. Makes it twitchy.
Can make it unstable in a straight line. Yeah,
Ugh.
very darty. And if you need a lot of toe out, it might point to an underlying Ackerman issue.
Okay, rear toe.
Yeah.
Usually a little bit of toe in for drift cars.
Yes, this is pretty standard. Rear toe in provides stability under throttle, helps with drive or forward propulsion.
How does it help drive when sliding? You said it plants the tire harder.
It does. The tires are slightly fighting each other, pointing inwards. This creates a bit of scrub that actually generates forward thrust, even while spinning. Helps convert rotational energy into forward motion, plants the tire, gives more controlled acceleration.
And the advice is never want any toe out in the rear. Why is rear toe out so bad?
Oh, it makes the car incredibly unstable. Wants to swap ends constantly, slides too easily, almost uncontrollably, kills drive, kills predictability, just makes it handful.
Baseline for rear,
Mm-hmm.
an 1/8 toe in total, across both wheels.
Good starting point. Measured across the pair, yeah, not per side.
And like camber, toe can change dynamically with suspension travel, bump steer related.
Absolutely. Some cars bump in or bump out, change toe under compression or droop. A Corvette's rack position causes more dynamic toe change than some BMWs or Supras, for example. Tuners need to account for that.
All right, this is where it gets really complex. Ackerman steering geometry. The difference in angle between the inside and outside wheel when turning.
Yeah, the geometry dance. It's a principle, not a specific car problem.
So normal cars, street cars, grip cars, they all use positive Ackerman. Inside wheel turns sharper.
Correct. Because geometrically, in a normal turn, the inside wheel travels a tighter radius circle. Positive Ackerman minimizes tire scrubbing, maximizes grip when both tires are rolling relatively cleanly.
But drifting screws with that geometry because the car is rotating differently.
Exactly. The pivot point changes. So negative or reverse Ackerman, where the outside trail wheel turns sharper, is sometimes considered more geometrically correct for drifting.
Why? Because the outside wheel is traveling a shorter arc relative to the drift's rotation point.
That's the theory. It allows both front tires to track more cleanly at angle, reducing scrub, making it easier to hold deep angle.
But it's horrendous on the street.
Yeah, because in normal low-angle turns, it causes massive scrubbing. Feels awful, wears tires weirdly.
Then there's parallel or zero Ackerman, where both wheels turn about the same angle at full lock.
Right. A common target for drift setups. Though achieving true parallel steering throughout the entire range is basically impossible with normal racks due to the geometry, but close to parallel at lock is achievable.
So how do you adjust this? Modifying knuckles is common first step. Redrilling, cut and shut.
Yep. Common DIY or entry-level mod to get more angle, but it often increases positive Ackerman.
Which means more scrubbing at full lock, faster tire wear on that lead front.
Exactly. You get the angle, but it's not necessarily efficient angle. Burns up that inside edge of the lead tire.
So better solutions involve rack relocation or offset spacers.
Yeah, moving the rack or using offset spacers changes the inner tie rod pickup points relative to the chassis. This alters the tie rod angles and can reduce that unwanted dynamic toe-out or Ackerman effect. Rack relocation is cleaner, but harder. Spacers are easier.
And the high-end solution is purpose-built knuckles, like FDF, WiseFab.
Those are the game changers. They have adjustable Ackerman plates. Tiny adjustments to the tie rod pickup point on those plates, just millimeters, can make huge differences in Ackerman angle at lock, like 20 degrees difference from a tiny shift.
Wow, incredible precision.
It allows teams to really fine-tune it for the driver, the track, everything.
And the best Ackerman is subjective. Driver preference, track specific.
Hugely. Some pros like some positive Ackerman, especially for initiation feel, maybe on banked tracks where the trail wheel is unloaded anyway. Others prefer near zero or negative anti-Ackerman for that no scrubbing force feel, requiring more direct input but potentially better tire wear at angle.
And track layout matters. Big bangs versus tight courses.
Definitely. Irwindale's I-banks might favor one setup, while a small, flat go-kart track might favor another completely. It's all about optimizing tire wear and car behavior for that specific environment.
Okay, moving on. Kingpin inclination, KPI, or steering axis inclination, SAI.
Yeah.
Angle of the steering pivot line viewed from the front.
Another critical, often overlooked angle.
And it significantly affects how the wheel behaves when you turn. Lengthening the lower control arm for angle often increases KPI.
Yes, quite significantly sometimes.
And high KPI can lead to wheel flop. The lead wheel gains a lot of positive camber at full lock.
Exactly. The wheel literally looks like it's flopping over onto its outside edge. Kills your contact patch right when you need steering grip most at full lock. Makes it feel unpredictable.
Whereas lower KPI, maybe from specifically designed kits, keeps the lead wheel flatter at lock.
Correct. You get a much more consistent contact patch throughout the steering range, especially at high angles, more predictable grip.
So this is fascinating. Two cars, same static camber, caster, toe, can handle totally differently because of KPI.
Absolutely. KPI is that unseen difference. It dictates the dynamic camber change and scrub radius as you steer. It's why just copying alignment numbers doesn't always work. You need to understand the underlying geometry like KPI.
Next, roll center. The theoretical point the chassis pivots around during cornering, determined by suspension geometry.
Yeah, imaginary point, but with very real effects.
And lowering a car a lot, like drift cars often are, pushes the roll center way down, often below ground.
Common side effect of slamming a car, yeah. The control arm angles change dramatically.
And why is a super low roll center bad? Relationship to center of gravity?
Right. The distance between the center of gravity where the car's mass is centered and the roll center acts like a lever arm. Bigger distance, more leverage for body roll.
So low roll center equals lots of body roll potential.
Exactly. Makes the car feel softer, more roll prone. A higher roll center reduces that leverage, makes the car inherently stiffer against roll.
So roll center correction parts, like drop knuckles, aim to fix this.
Precisely. They raise the spindle mounting point relative to the control arm points. This lets you lower the car physically, but keeps the suspension geometry closer to stock, maintaining a higher, more favorable roll center.
And sway bars work with the roll center height to manage the final amount of roll?
Absolutely, they're partners. You tune roll center geometrically, then fine-tune the dynamic roll resistance with your sway bars and spring shocks. It's about getting the right balance of roll for weight transfer without excessive uncontrolled body movement.
Last geometry point, bump steer. Unwanted toe change as the suspension moves up and down.
The nasty one. Wheel steers itself over bumps without you turning the wheel.
Caused by caster changes, angle kits, roll center mods, basically messing with the front suspension geometry.
Yeah, it's all interconnected. Fundamentally, it happens when the tie rod and the lower control arm don't swing through perfectly parallel arcs.
So as the suspension compresses, the tie rod pulls or pushes the steering arm, changing the toe.
Exactly. Makes the car twitchy, unpredictable, especially hitting bumps mid-corner. Really unsettling.
How do you fix it?
Good aftermarket angle kits are often designed to minimize bump steer within their intended operating range. Adjusting steering rack height or using specific tie rod ends can also help align the tie rod's arc more closely with the control arm's arc. It's about making those two arcs as parallel as possible through the suspension travel.
Okay, if we tie all this together, It's clear there's no single perfect setup. It's so dependent on the car, the driver, the track.
Exactly. No magic numbers.
Mm.
What works for Forsberg might not work for Denofa, might not work for you.
So how do you find what's right for you?
Simple answer, testing. Lots of it. You need to go test it a lot.
Not just theory, seat time.
Absolutely. Suspension tuning takes a lot of testing and just drive time and understanding what you're feeling from the seat of your pants. Experienced drivers can feel tiny changes.
That slight change in initiation feel or how it holds angle?
Exactly. And you need to correlate that feeling back to the adjustment you just made.
Even small adjustments at the track, like changing a sway bar hole.
Yeah, you can do that on the fly, between runs, feel the difference immediately. Did it help? Did it hurt? That instant feedback loop is invaluable.
So start with a baseline. Neutral settings, adjustable arms, equal length, side to side.
Good practice. Get everything square and neutral first. Then make one small incremental change at a time.
One change, test, evaluate. Don't change 5 things at once.
Please don't. You'll never know what actually did what. And crucially, always end with setting your toe after any caster or camber adjustment.
Because changing caster or camber will affect your toe setting.
Always. So toe is the last step in the sequence.
And ultimately, the goal is finding what's comfortable for you, the driver.
That's huge. A setup that inspires confidence in you will make you faster and more consistent than a theoretically perfect setup that feels weird or unpredictable to you.
Yeah.
Happy driver, fast driver.
And maybe tweak other things first. Tire pressure, shock damping.
Yeah, before you start making big alignment changes, try the easy stuff.
Oh.
Sometimes slightly adjusting tire pressure or clicker settings on your shocks can fix the handling issue without messing with your core alignment.
Can you do useful stuff trackside without a fancy alignment rig?
Definitely. Reading tire wear is huge. If the inside edge is burning off, maybe dial back a bit of negative camber. Outside edge wearing, maybe add a bit. Aim for even wear across the tread. That means you're maximizing the contact patch and tire life. Adjust on the fly.
You can even measure stuff yourself. Steering angle, dynamic toe.
Yeah, basic tools work. Lift the car safely, use angle finders, tape measures, string. You can get pretty close. Trace the rotor movement, measure angles.
Checking for binding, too. Removing the spring and cycling the suspension.
Essential diagnostic. Feel for any tight spots, catches, resistance as you move the suspension through its full travel. Should be smooth. Binding kills performance.
And after any oopsie, any off-track excursion, check toe first.
Immediately. Grab the toe plates. Toe is usually the first thing to get knocked out of whack if you bend something slightly. Quickest way to check for damage.
And always align on level ground, sway bars disconnected, equal tire pressures.
Critical for accuracy. Eliminate as many variables as possible.
Beyond the geometry itself, tires. They make the biggest difference.
Absolutely paramount. Your only connection to the ground. Investing in good front tires like sticky 200 treadwear autocross types is a really good investment.
Why front tires specifically if the rears are doing the sliding?
Because the fronts are doing the steering. They control your entry, your angle, your line. Good front grip gives you precision, confidence, allows you to place the car accurately. Cheap fronts mean vague steering, understeer, fighting the car.
Makes sense. And power steering. Seems essential with those crazy steering ratios and fast corrections.
Yeah, vital. Imagine trying to muscle one of these cars lock to lock at speed without it. Dai Yoshihara's car, 1.5 turns lock to lock, insane 4.1 ratio. Needs power assist.
Traditional hydraulic systems can have issues, though. Fluid boiling, cavitation.
Yeah, especially under prolonged stress, like sitting in staging lanes for hours, engine running hot, can make the steering feel weak or inconsistent right when you need it.
Which is why electric power steering, EPS, is becoming more common.
Increasingly so. No drag on the engine from a pump belt. Less fluid to overheat. Can offer adjustable assist levels. Integrates with stability systems. It's the modern solution. Really enables the extreme steering setups we see now.
Wow, okay, what a journey through the suspension maze. From literally fixing rust on that Datsun to get a solid base.
Right back to the fundamentals.
All the way to the super nuanced science behind camber, caster, toe, Ackerman, KPI, roll fenders. It really is a symphony of adjustments.
It truly is. Every single component, springs, shocks, bars, knuckles, arms, all those angles, they all play a critical role in creating that controlled slide.
It's pretty amazing how they make it look so effortless sometimes.
Yeah, and I think if we connect this to the bigger picture, what really stands out is that there isn't one single perfect recipe, right?
Yeah, magic formula.
It's this dynamic, always evolving process. It combines solid engineering principles, sure, but also requires tons of testing, iteration, and ultimately it comes down to the driver's feel. What works for them?
So the goal isn't just to copy someone else's setup sheet.
Exactly. It's about empowering you, the listener, to understand the why behind each adjustment. Why does changing caster do that? Why is Ackerman important here? So you can interpret what your car is telling you and make smart choices.
So what does this all mean for you listening? Well, understanding these details isn't just for pro drivers or engineers building Formula Drift cars.
Not at all.
It's about gaining a much deeper appreciation for these incredible machines, the engineering involved, and maybe, just maybe, applying that whole give-and-take philosophy elsewhere.
Interesting thought. That balancing act applies to a lot of complex systems.
Yeah, so consider this. If these seemingly tiny fractional adjustments in suspension geometry, a degree here, a millimeter there, can unlock such huge changes in performance and predictability, even in how long your tires last. What subtle tweaks, what deeper understandings might you uncover in your own pursuits, whatever they may be? Where could a little bit of deep dive knowledge lead to surprising new levels of control and mastery for you?
Something to think about.
Definitely something to mull over till next time.